What's going on, smart people? Bringing you a video on perturbation theory today. This one's a mouthful because today we're going to be talking about first-order, non-degenerate, time-independent perturbation theory. I'm going to be showing you how to derive the expressions for the corrections to the energies as well as the wave functions. Now with perturbation theory, it's a fantastic way oftentimes to find out what the answer almost is. You have some problem that looks like one that you know how to solve, but it's a little bit different. So you say, well, maybe it's equal to the one I know how to solve plus a series of corrections. Now, whether or not that series actually converges to the right answer is a topic for another video. If you guys want to see like convergence of perturbative series in a future video, let me know. But today, I'm assuming maybe you need help with your quantum homework, so you're working with potentials to where it definitely converges to the correct answer, and maybe first order is all you really need. So to put this stuff into writing, we have some eigenproblem. We have our Schrodinger equation. We have the Hamiltonian acting on our energy eigenstates equal to our energies times those eigenstates. It's the definition of an eigenvalue problem. And I'm saying that this Hamiltonian can be expressed in terms of one that I know how to solve, so the Hamiltonian to a problem that you've solved before, plus some perturbation, plus some, I'll call it H1, something that's a little bit harder to work with, and maybe you don't know how to solve this problem exactly anymore. So what perturbation theory says is, well, maybe these energies are in terms of the energies that I do know how to solve plus an infinite chain of correcting terms, and the same goes for the wave functions. So what I'm saying here is I'm saying that my energies are just we're going to be doing kind of a power series over some variable lambda, so a sum over I equal to 0 to infinity of what we know how to solve plus our correcting terms. So lambda to the I en parentheses I. So what this means is for I equal to 0, we just get our regular energy that we know how to solve. That's the solution for this Hamiltonian, plus all of those correcting terms, and the same is going to go for our wave function. En is equal to the sum over I equal to 0 to infinity lambda I eni. Okay. Now, when we actually we're going to substitute this into our Schrodinger equation, and when we do that, we're going to be careful not to use the same index twice, because there's going to be different combinations of these that we can use, and using I twice eliminates part of the problem. So let's go ahead and do that. Let's go ahead and substitute in our power series expressions for our energies and our energy eigenstates into our Schrodinger equation. And to make things clear, lambda is some parameter that we're going to set equal to 1 anyway. So I'm going to go ahead and parameterize this perturbing potential as well with the factor of lambda. And what we're going to do is we're just going to substitute this back into our Schrodinger equation. So we do that, and we get h0 plus lambda h1 times our eigenstates, and since we're using this one first, this one gets to be called I, sum over I. So this parentheses up here doesn't mean that I'm exponentiating anything. This is the order of the correction. So for I equal to 0, that's the unperturbed eigenstate. I equal to 1 is the first order correction, and we're going to get to that in just a bit. So this should be equal to substituting this stuff in here, and now we have double sum. So we're going to have a sum over I and a sum over another index that I'll call j. I equals 0 to infinity, j equals 0 to infinity. And then both of these are going to have a factor of lambda. So we'll have a lambda I. So this lambda I corresponds to the wave function, and this lambda j corresponds to the energies. So we're going to have an en j ket en I. So if we called them the same things, we would just get contributions of I equal to j, and we'd be losing some of these cross terms that we could have. Before we go any further, I think it's probably instructive to talk about what we have here so far and how to interpret this thing, what we can assume and what we can impose. So far assuming this series converges, this actually isn't perturbative yet. This becomes perturbative once we truncate our series at exactly less than infinity. But right now, this is not perturbative, this is exact. What we're going to do is we're only going to go up to first order in lambda, hence why we call it first order perturbation theory. Some assumptions that we're making is that there's only going to be one eigenstate that gives us that unique E sub n. So this is what we're saying when we say that this is non-degenerate perturbation theory. So this is going to be unique for each E sub n. Okay, for our unperturbed eigenstate, E sub n, this forms a basis. This forms a complete basis. Any vector in this Hilbert space we can describe as a linear combination of these E sub n. And that even goes for our perturbed states. So in other words, we can describe some E sub n I, so the ith correction to the eigenstates, as a linear combination of those basis vectors. So sum over, say, m of our basis vectors in the unperturbed basis vectors, E m0 times our transformation coefficients, times our E m0 E n I. Now if you're, so this is the prime example of when people say linear algebra is very important in quantum mechanics. This is a great example of where it actually pops up, because first of all, if you don't know what this is, if you don't really know what a transformation coefficient is, it could be a bit confusing, especially if Dirac notation is new to you. But all this is saying is, say we were to have some vector A, which is just some combination of ax, e sub x, plus ay, e sub y, you get the idea, plus a z component. I can pick out the components of this vector by taking the dot product with the basis vector. If I were to do e sub x dot a, that would give me a sub x, and so on. So in bracket notation for this is just saying, if I were to let, say, x be my e sub x basis vector and so on, I can describe my a vector equal to a sum over I of my basis vector times the actual vector a, and then described in terms of these bases. So that's all I'm saying. This is the exact same thing, only we've generalized to complex dot products that may or may not be continuous and described in terms of integrals or whatever. Okay, so that's all that this is doing here. These are just the coefficients attached to my basis vector. For those of you who may not have been too comfortable with linear algebra. So this is actually going to be important later on, once we actually want to know what our corrections to our wave functions actually are. Okay? Now one thing that we're going to impose, and we have the freedom to do so, is a normalization condition. We're probably used to normalizations where you take the inner product of your total wave function and you set it equal to 1. We're going to choose a slightly different one. We're assuming perturbation theory is fine, which means the first order correction, or sorry, rather the unperturbed eigenstate is probably not that far off from the full wave function itself. So what we're going to do is also impose that the unperturbed wave function inner product with the full one is equal to 1. Okay, and this might be a little bit confusing. Why are we doing this? It makes our calculations simpler later. We can always renormalize our states in the future, and if our perturbation is small, then this is fine. And if we expand this out, so this is going to be equal to, if we're taking a look at our series expansion here, we know what E sub n is. It's just this power series. So this is just going to be equal to the sum over I of lambda I en0 en I equal to 0 to infinity. And for I equal to 0, we could just write out a couple of the terms already. So this is just going to be equal, lambda to the 0 is just 1. And then these are just going to be equal to each other for I equal to 0. So this is already 1, plus the next factor of lambda equal to 1. Plus dot dot dot. And we already have our condition satisfied for the first term, which means that all of these inner products for any power of lambda where the order of the correction is not equal, those must be equal to 0. So these terms are all 0. So if we have non-matching orders of our correction, these inner products are going to be 0. And that's also going to be important. But I think we've more or less established the ground rules. So let's get to actually doing some perturbation theory. Let's find these first order corrections. Okay, I'm going to keep this up here because it'll be nice to identify that later once we're correcting wave functions. So we're interested in first order, which means we're only going to first order in lambda. So let's go ahead and expand that out. So this is just going to be an h0 plus lambda h1. And I equal to 0 is just going to give us an e n0 plus lambda e n1. And then now the next side, so this is going to be, so for both of them equal to 0, that's just going to give us our unperturbed wave function. So this is just going to be an e n0 e n0. So you can think of this so far as just 0 with order and lambda, so we haven't actually done anything perturbative yet, plus, and I'm going to factor out a power of lambda, and we can have different combinations of I and j that both give us first order and lambda, which is why it's important that we made the distinction between the summation index. So either we can have I equal to 1 and j equal to 0, or vice versa. So we can have, if I equals 1, j equals 0, then we have e n0 e n1 plus, and then if we flip that, then it's going to be e n1 e n0. And that's going to be the pattern for any order of perturbation theory that you go through. The coefficients times the state, the order should sum to whatever your power of lambda is. Okay, let's go ahead and distribute this out real quick. So we have h0 e sub n 0 plus, let's also pull out our factors of lambda. So to first order lambda, we can have h1 e n0 and then we can also have h0 e n1. Okay, and actually in this case we already have lambda squared, but since we're only dealing with first order perturbation theory, we're not even going to write it because that'd be stupid. So normally there would be that lambda squared whatever, but forget about it. Forget about it. Okay, now we are at the liberty of equating powers in lambda, just like you would do in your differential equations class. So for 0th order, so once where we do not have a lambda in front, we have h0 e n0 is equal to e n0 e n0, which just means we haven't done anything yet because this is just the unperturbed eigenproblem. This is the one you already know how to solve. So this is just saying, yeah, the 0th order correction is if you just pretend like that perturbation isn't even there. That's not very helpful. Now to first order, so we're equating first powers of lambda. We have h1 e n0 plus h0 e n1 is equal to e n0 e n1 plus e n1 e n0. I think I'm losing my voice. Great. Well, now we don't actually need this anymore, and I'm probably going to need some real estate soon, so I'm going to erase this part and hope I don't regret it. Okay, so now we have an explicit first order correction to the energy written out in our first order perturbation theory, so that's good. That's a good sign. Now we just want to isolate it. How do we get that by itself? Well, we can get it by itself by taking the inner product with the unperturbed eigenstate. So we're going to take the inner product, we're going to sandwich all this in between the bra En0. Okay? And I'm also going to get rid of this. You get the idea. This goes on forever. Okay. So this is just going to be En0 H1 En0 plus En0 H0 En1, which is going to be equal to, now I could go ahead, I could sandwich in, these are just numbers, right? They can be pulled outside of that inner product. And if we do that, so we have an En0 En1, sorry, En0 En1, our normalization condition tells us that this has to be equal 0 because the order of the correction doesn't match. So this whole term is 0. Why even write it? And then for this one is fine. En0.En0 is just going to give us 1 by orthonormality. So we have this is equal to En1. Okay. The Hamiltonian operator is Hermitian, which means we can have it acting to the right or to the left. And when we pull this guy, if we have him act on this eigenstate, we just get an En0, and then we get an En0.En1, so this term also goes to 0. So that what that tells us is that, I'm just going to write it right now, the first order correction to the energy is equal to just the expectation value of our perturbation. So when you're doing perturbation theory, ideally you know what this is. This is the problem you know how to solve, and you're given your potential. So all you have to do is sandwich in your perturbing potential into our unperturbed eigenstates, and that'll give you the first order correction to your energy. One comment I want to make about this is if someone says, give me a better approximation for our energy than the unperturbed, this is not exactly your answer yet because you still have to add it to the original unperturbed energy. So your real first order correction would be this plus E0. Okay, so that's our first order correction to the energy. I'm going to erase some of this, that way we can find the correction to the wave function. So I've just moved everything up. The next thing that I want to do is I want to explicitly find this En1. And what I'm going to do that is I'm going to take the inner product with this bra vector, that's going to be, that's a ket, with em0, where I'm going to be imposing that m does not equal n. So let's go ahead and do that. We get em0 h1 en0 plus em0 h0 en1 is equal to, these are just numbers, so I'm going to pull them out. So we got En0 En0 En1. And with this last term, I'm taking the inner product m and n, where n does not equal m, so this term would go to 0 because I'm taking because they're orthogonal. So this last term I'm not even going to write. Okay, now I can also have this act to the left to give me that eigenvalue. So this is just going to become em0 h1 en0 plus em0 em0 en1, which is equal to en0 em0 en1. Okay, and then I could bring this term over and factor out this term here, so we get em0 h1 en0 is equal to en0 minus em0 En0, En0. We'll go ahead and divide this term over. So that's just going to become En0 minus Em0 is equal to okay, and it looks like, well, this is just a number, right? This isn't actually a vector like we were hoping to find. But if we look up here, we get exactly something that looks like our transformation coefficient that we wanted to express our perturbed state in terms of with respect to the unperturbed basis vectors. So we can actually write, if we substitute I equal to 1, this becomes our sum over m with just exactly these transformation coefficients. So in a sense, these are just transformation coefficients for representing our first order correction to the wave function in terms of the unperturbed wave function. So we get that En1 vector is just equal to the sum over m not equal to n of Em0, H1, En0 divided by En0 minus Em0 times our unperturbed Em0. And there we have it. So we've just derived the first order corrections to the energies and the wave functions in a first order non-degenerate time-independent perturbation theory. And again, for degenerate theory, this wouldn't hold because we could have different eigenstates that correspond to the same eigenvalue. So we could have some En equal to Em, and we'd get a 0 in the denominator. That doesn't work. So for degeneracy, we need something a bit more robust. But maybe in a future video, you'd like to see me go over degenerate theory, maybe just higher order in non-degenerate theory like second order, or maybe even time dependent, who knows. I think this stuff is pretty fun because it's so much linear algebra and it's my favorite, but I understand that if this is your first time in quantum mechanics, maybe linear isn't your strong suit yet, and not to mention doing linear in abstract bracket notation, so I understand, but maybe seeing my videos is good practice for you. So let me know in the comment section if you'd like to see more of it, and I will see you guys there.